Welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So dear students, this is a very special quick revision series in which we shall be doing the entire chapter in just 10 minutes, right? So that your time gets saved a lot. So in this particular session, I'm going to discuss the complete states of matter chapter with you in just 10 minutes, dear students, right? But before that, if you have not subscribed to the channel yet, please do subscribe to the channel. Let this Unacademy NEET English channel grow exponentially the way it's happening right now, okay? Alright, so let's get going. Let's get started with the first topic, that's Boyle's law over here. So first thing, my dear students, which I would want all of you to remember, Boyle's law is valid for an ideal gas when the number of moles and temperature of the gas is kept constant. And as per Boyle's law is concerned, pressure of the gas is inversely proportional to volume of the gas, right? Since pressure and volume, these are inversely proportional to each other. So if you want to plot a graph between pressure and volume, the nature of the graph is going to be rectangular hyperbola. And this hyperbola is made when the temperature of the gas is kept constant, and you call this graph over here as the isotherm, number one. Number two, if you remove this proportionality sign over here, you'll get a constant, and the value of that particular constant is going to be nRT. Okay. Similarly, dear students, if you draw the pressure volume curves, the different pressure volume curves you have drawn at different temperatures. So which temperature is going to be more? This T1 temperature is always going to be more than that of T2, more than that of T3. Similarly, when you talk about the Charles law is applicable to an ideal gas when number of moles and pressure of the gas is kept constant. And as per Charles law is concerned, volume of the gas is directly proportional to temperature of the gas in Kelvin. As simple as that. If you remove the proportionality sign, you'll be getting a constant whose value is nR divided by P. Since volume is directly proportional to temperature in Kelvin, so if you want to plot a graph between volume and temperature, it's going to be a straight line, right? Okay. Similarly, if you draw 2-3 straight lines like this at different pressures P1, P2, P3, this particular P1 is going to be more than that of P2, more than that of P3, right? And this particular graph, which is made at constant pressure, you call this graph as the isobar over here. Similarly, if you look at the Gay-Lussac's law, Gay-Lussac's law is valid for the ideal gas, which is kept when Gay-Lussac's law is applicable for the gas when number of moles and volume of the gas is kept fixed. So Gay-Lussac's law says that pressure of the gas is directly proportional to temperature of the gas in Kelvin. Again, if you remove the proportionality sign, you'll be getting a constant whose value is nR divided by V, right? And dear students, if you want to plot a graph between pressure and temperature in Kelvin, it's again going to be a straight line, which is made when volume of the gas is kept constant, and you call this particular curve as the isochord. Similarly, if you draw like 2-3 graphs between pressure and temperature, kept at different volumes, which volume is always going to be more? V1 will be more than that of V2, will be more than that of V3. Similarly, if you look at the Avogadro's law again is valid only when pressure and temperature of the gas is kept fixed. And as per Avogadro's law, volume of the gas is directly proportional to number of moles of the gas. As simple as that. If you remove the proportionality, you'll be getting a constant whose value is equal to RT divided by P. And similarly, since volume is directly proportional to moles, right, if you want to plot a graph, it's going to be a straight line like this. Okay. Now people, if you will combine Boyle's law, Charles' law and Avogadro's law, you will be getting one particular equation that gives the combined effect of all the gas equations, right? And this particular equation over here is something which you call as ideal gas equation. PV is equal to nRT. The R over here, this is something which you call as universal gas constant, whose value depends on the units of pressure and volume. R has got 3 values exactly. One is 8.314 joules per Kelvin per mole, 0.0821 atm liter per Kelvin per mole, 1.98 calories per Kelvin per mole. There is one more form of the ideal gas equation, that is the density form, which is Pm is equal to dRT, where P stands for pressure, M molar mass of the gas, D stands for the density of the gas, and R is the again gas constant, T is the temperature. One more thing, in order to minimize your calculations, instead of 8.314, you can just write 25 divided by 3. Instead of this particular 0.0821, you can just write 1 divided by 12. Right? And instead of 1.98, just to reduce the calculations, you can take the value exactly as 2. Now there is one more important topic, that's what you call as Dalton's law. Dalton's law First of all, whenever you have got two or more than two chemically non-reacting gases present in the same container, the total pressure of the mixture, the total pressure of the gaseous mixture is the sum of the partial pressures of the individual gases. Now the point is, how do we calculate the total pressure of the mixture? Simple, RT divided by V multiplied by the total moles present in this particular mixture. The total moles present in this particular mixture. Similarly, if they ask you to calculate the partial pressure of, for example, gas A, partial pressure of gas B, partial pressure of A is nothing, it is just the total pressure of the mixture multiplied by mole fraction of A. Partial pressure of B is total pressure of the mixture multiplied by mole fraction of B. That's all, right? Similarly, if you want to have a look on the Graham's law, right? Again, one more important topic. As far as this particular Graham's law is concerned, rate of effusion is inversely proportional to square root of molar mass of the gas. More the molar mass of the gas, lesser is going to be the rate of effusion of the gas. Now, for example, you have got two gases A and B, right? Let's assume I'm keeping the pressure and temperature of these gases same. Molar mass of gas A is Ma, molar mass of gas B is Mb, right? Let's say VA/ml of gas A comes out of the container in Ta time. Similarly, VB/ml of gas B is coming out of the container in time Tb. Let's say I need to compare the rates of effusions of these two gases. How am I going to do it? Rate of effusion of A divided by rate of effusion of B is equal to under root of molar mass of B divided by molar mass of A. Instead of rate of effusion of A, you can write volume of A coming out of the container divided by time taken by A. Similarly, instead of rate of effusion of B, you can write volume of B coming out of the container divided by time taken by B. Similarly, if they ask you to calculate the kinetic energy, the average translational kinetic energy for 1 mole of the gas. Kinetic energy, which is the average translational kinetic energy for 1 mole of the gas, it's just going to be 3 divided by 2 RT, right? For 1 molecule, if they ask, it's going to be 3 divided by 2 kT, where K stands for the Boltzmann's constant. If they ask you to calculate the average translational kinetic energy for n moles of the gas, it's going to be 3 divided by 2 nRT. Similarly, we have got different types of molecular speeds as well. One is called as RMS speed, one is called as average speed, most probable speed. These are the results by means of which you can calculate these different speeds, right? And at the same time, for a particular gas kept at a particular temperature, Vrms is always greater than that of V average, which is greater than that of most probable speed, right? Similarly, the most important part of the chapter, that's van der Waals gas equation. This is your van der Waals gas equation, P plus AN square by V square, V minus NB is equal to nRT. My dear students, this particular term is called as volume correction factor, and this particular term is called as pressure correction factor. Over here you get two constants A and B, which you call as the van der Waals constants. Let me tell you, this A, it gives us the idea about the force of attraction between the gas molecules. More the value of A for a gas, more is going to be the force of attraction between the gas molecules. Similarly, this B gives us the idea about the size of the gas molecules. More the value of B, more is going to be the size of the gas molecules, right? Similarly, if you ask me about the units of A and B, the unit of A is going to be atm liter square per mole square. Similarly, if you ask me about the unit of B, it's going to be liter per mole. And mathematically, this B is always equal to 4 multiplied by 4 by 3 pi r cube multiplied by Avogadro's number, where R stands for the radius of the gas molecule, right? Or you can define B in this way as well. B is equal to 4 multiplied by actual volume of 1 mole of gas, right? Similarly, when you talk about the compressibility factor, we have got different ways to calculate compressibility factor. One is V naught divided by Vi. Observed volume of the gas divided by ideal volume of the gas. One is PV divided by nRT. One is PM divided by dRT. That particular gas whose Z value will be equal to 1, you call that gas as the ideal gas. Z value less than 1, the gas is going to be real, in which force of attraction dominates. Z greater than 1, the gas is again going to be real, force of repulsion dominates. At low pressure, the value of Z is exactly equal to 1 minus A by VRT. At high pressure, it's going to be 1 plus PB divided by RT. That means here it's less than 1, here it's greater than 1. That means here attractive force is dominating, here repulsive forces will be dominating, right? Similarly, there are a few more terminologies. This is how you calculate critical temperature, right? That temperature above which a gas cannot be liquefied, howsoever pressure can be applied. Similarly, critical pressure, this is the formula. Critical volume, this is the formula. Where A and B, you already know, these are the van der Waals constants. And if they ask you to calculate the compressibility factor of the gas under critical conditions. Do remember its value directly is going to be 3 divided by 8. So this was a very quick revision of the chapter states of matter, and you can expect similar type of revision sessions in the upcoming days of your complete chemistry. With this, I'll be taking a leave. Take care, God bless you all, love you all, and if you have not liked the session yet, I would want you guys to like the session. I would want you guys to share this video, and I would want you guys to first of all subscribe to your Unacademy NEET English channel right now. Take care, God bless you all, and love you all. Bye-bye.